Have a spare banana? Throw it at a robot. Using Drake, a physics simulator that models real robot actuators and sensors, we created a system that can perceive a thrown object, predict its motion, plan a catching pose and trajectory, and execute it successfully. The system even works on a variety of objects and throws.
Most robots today are employed in heavy, slow tasks. However, robots that can perform dynamic behaviors have significant potential benefits. They can move objects faster at longer distances and with more style. Work in the area of throwing robots like CatchingBot has shown promising results, but works on catching robots are far and few and usually rely on complex grippers. We want to show that, with good planning, the complex dynamics of catching are possible even with limited hardware. Therefore, for our project, we've chosen to use the 7th degree of freedom KUKA arm and the WISE Robotics 2-finger WSG gripper. Our general strategy consists of three parts: perception, grasp selection, and motion planning. The perception system first uses iterative closest point to estimate the object's pose in the world frame at each time step, using the last pose predicted as an initial guess. This helps to speed up the ICP and make rotation prediction more stable. After we have collected enough pose guesses, we feed a fixed size window of predicted poses into our RunSec-based trajectory prediction algorithm. The algorithm randomly selects a pair of poses, which it uses to predict the parabolic trajectory and the rate of rotation of the object. It then calculates how many of the object's previous poses lie within some threshold of the trajectory, and the average error of those points from the trajectory. We then use the L2 norm as a metric for position and the spherical distance as a metric for rotation. Repeat this process several times, then choose the best trajectory guess as the output, based first on how many points lie on the trajectory, and based second on the average error.
Next, using the object's predicted trajectory, we plan a grasp. First, we sample 500 points from the object's point cloud and compute their Darboux frames to use as potential grasp poses. We also pick a time when the object is in the EWA's work envelope to perform the grasp. Then, of the 500 sampled grasps, we select the single best one by evaluating each grasp on three heuristics: strength, comfort, and catchability. Strength measures the distance between the y-axis of the grasp pose to the centroid of the object's point cloud using vector projections. Comfort measures whether the grasp points away from the world origin using vector dot products, making it easy for EWA to reach that position. Catchability measures whether the object can fly in between the gripper fingers, also using vector dot products. In the end, we come out with a good grasp pose for the gripper. Lastly, we plan a trajectory for EWA to get to the grasp pose and catch the object. To do this, we use a constrained optimization in joint configuration space. Our decision variables are 8 control points of a 7-dimensional B-spline. Our cost function is the length of the path, and we add constraints on the B-spline start and end poses and velocities, on the joint positions and velocities to be within EWA's limits, and constrain the duration of the trajectory to be precisely equal to the duration between now and the time the object is in the grasping position. Despite the power of nonlinear optimization solvers like SNOPT, this is a lot of constraints, so we need to give SNOPT a boost. First, we solve for a non-optimal trajectory using inverse kinematics and use this as an initial guess for SNOPT. We also solve the trajectory optimization multiple times with progressively tighter constraints. And every time step, as the object's predicted motion varies slightly, we use the last calculated trajectory as an initial guess for an updated trajectory. Now, just closing the grippers at the right time, it's working, well, not quite. The trajectory optimization is still failing, and after much debugging, we suspect it's due to the end velocity constraint that requires EWA and the object to have the same velocity at the catch. A bit of math later, we realize that we're basically asking EWA to reach the velocity of this banana from rest in less than a second. So, we need to modify this constraint. Instead of requiring EWA and the object's velocity to match at the catch, we just require the directions to match. And nice! It's still not working. The trajectory optimization is succeeding, but we noticed two new problems. One, the object was reaching the grasp pose before EWA was, and two, EWA was closing the gripper way too late. To address problem one, we switched to using an inverse dynamics controller to give EWA a feed-forward velocity and acceleration to track the trajectory more accurately. To address problem two, we simply start closing the gripper earlier. With a few other tweaks, we're finally actually getting objects to catch.
Let's just take a moment to admire how gracefully EWA grabs the banana. In the end, we were able to get the system working on a banana, a ball, and a mustard bottle when thrown in a graspable orientation. We also managed to throws from 2 to 4 meters away. In the future, we would like to increase robustness by controlling the grippers based on the object's position rather than just time alone. Additionally, we think that there exist better architectures for grasping and trajectory optimization. Our current system performs these tasks separately, but logically, these two tasks are actually very intertwined and could be solved as one optimization. Finally, we'd like to explore the challenge of catching objects with difficult and non-constant rotations, forcing Iwa to use different grasping strategy like this one, which we think would be achieved with more clever optimization constraints. Thank you for coming on this journey with us.